My name is Lindy Humphrey, and this is my Lab 3 for Physics 2211 for black holes. To introduce this lab, it is set up into two parts and two main purposes. The first is to determine the mass of the black hole by analyzing a star's motion through a glow script code we generated. The second was to use that mass that we calculated in the first part and determine the initial velocity a spaceship has to travel without crashing into the black hole or the planet that it was leaving from and still escape. Some fundamental principles we will cover in this lab include Newton's second law of motion and the universal law of gravitation. And to give an overview of the results for this lab, we were able to determine that the mass of the black hole was 8.6 e33 kilograms, and the initial velocity of the spaceship was this vector shown here. Universal gravitation is represented by this equation right here, and then Newton's second law of motion, also known as the momentum principle, is change in momentum over time and is equal to its perpendicular and parallel components. We can also get the velocity update formula and the position formula out of Newton's second law shown here. I'll also go ahead and make a note that the system in this lab is the star and the surroundings is the black hole. To evaluate, we are using glow script code, and I'll show everything that I needed to plug in, and it also has our initial conditions. First, we have to plug in the mass of the star, which was given to us to be 2e to the 30th, and we have to change our delta t to 86,400, representing a full day in seconds. We also have our gravitational constant, which is 6.7 e to the negative 11th. To get the initial and final momentum, we have to multiply the mass of the star by its velocity components, shown in lines 164 and 165. In 168 and 69, we calculated the change in velocity and momentum by plugging in first v final minus v initial and p final minus p initial, typed in delta p over delta t. And we plugged that into FNet along with a few other equations shown here, which all leads to calculating the mass of the black hole in line 193. Then we run this code and we are given a unique trajectory of the star shown here. The magnitude of FNet is 8.3 e to the 28th, and the magnitude of FNet parallel is 3.07 e to the 28th, and the magnitude of FNet perp is 7.7 e to the 28th, and the mass of the black hole is 8.6 e to the 33rd. Now we can start the second part of this lab, which is calculating the initial velocity needed for the spaceship not to crash. We have a second glow script code that we have to use to evaluate the spaceship and its needed velocity for the second part of this lab, and we need to fill in a few details. First, we had to fill in the mass of the black hole from the first part of the lab, and then we cannot change these other constants below, but they are important to know. And then we also have our equations to find the speed and velocity of the planet initially. Then we are filling in our equations to find the net forces acting on the planet, shown here, and the forces acting on the ship in these lines. And the reason we are filling these in is to figure out the motion of both of our systems over time, or iterating the position and velocity from the net force. From that code, we are able to find the initial velocity of the ship, shown here, after doing a few trial and errors, plugging in our values for the x and y components in the code. A few possible sources of error, however, could have been that the mass of the black hole that we got from the first part of the lab we calculated was an average value based on all the data points it gave us, and instead of an exact value, and how different times can make the speed more accurate. To answer our discussion questions, the first question asks, how does the net force and its parallel and perpendicular components differ from the rate of change in momentum and its parallel and perpendicular components? The net force is equal to the change in momentum over time and is proportional to acceleration. So the net force and the perpendicular and parallel components are responsible for dictating or influencing the rate of change in direction and velocity. And then what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole and then escape? Ultimately, the velocity would have to be greater to account for more change in direction, because the perpendicular component formula, which is mv squared over radius, the change in the perpendicular component would be higher as it would be orbiting more. So it would need to be able to orbit the black hole without crashing, meaning it would have to be greater. Thank you.